Hi, this is Professor Cummings, and this is a lecture 2 for Module 1 in Lean Six Sigma. And in this particular lecture, we're going to go over the basics or the fundamentals of Six Sigma. So, lecture 1 was giving you an overview of Lean. Lecture 2 is giving you an overview of Six Sigma. And in lecture 3, we'll kind of show you the synergy between the two. So, Six Sigma in and of itself is a continuous improvement process, continuous improvement philosophy that has been used by several companies over the last 20 or 30 years, and it's a very successful one. It actually is focused more on reducing variation and problem solving and getting to the root cause of quality issues, more so than eliminating waste. And what I want to do in this particular lecture was give you an overview of how it's used, and as well as like why it's actually called Six Sigma. You know what that means and what the significance of that is. So, what is Six Sigma? So, it is a statistical-based methodology used to reduce variation and eliminate defects in business transactions and manufacturing processes. So that's the dictionary definition. So basically what that is saying is it's a data-driven process that helps you reduce the variation and eliminate your defects. So eliminate your defects, eliminate your problems, help you give your customer a more satisfactory experience. So that is the definition of Lean Six Sigma. But to give you a little bit of background, this started with an engineer named Walter Shewhart. And what Walter Shewhart did was very simple, but also pretty impressive. He recognized that processes, follow a predictable variation. And, the deviations from the variation could be assigned to some sort of a cause. So again, I'm just read that slide. So what does that mean fundamentally is that if you do something consistently and randomly, without any sort of intervention to it, or without deliberately changing the process, you will end up forming a natural bell curve, a normal bell curve. So you end up with a normal distribution of events. And when you think about it, that makes some sense, doesn't it? If you were to, make a drill press, or if you were, drilling holes with a drill press, you would expect to see that hole have a little bit of variation in size and diameter, or maybe even just variation in position a little bit. Nothing really dramatic, nothing really, over the top, but because there's going to be a little bit of slop in your bearings, a little bit of slop in the shank of the drill, a little bit of, play here and there throughout the process, a little bit of play in how you set the material into play, you will see some variation, even if it's happening on a very minute level. You can have the most fine-tuned machine, and if you measure it well enough, you will be able to see variation. And that's one of the ways in manufacturing processes that you consider a machine more or less capable than another. Two different, the same process happening on two different types of machine tools. And you'll see this, throughout nature, that things will form a normal distribution over time, even like with heights of people, with weights of people, things fall into a normal distribution. So there's going to be an average, and then there's going to be some variation from that average that becomes fairly predictable. And when things fall outside of that normal distribution, there's usually an assignable or special cause to it. There's usually some reason that happens. And we'll go through some examples of that. Now, Shewhart, he's considered the father of statistical process control, and he's the one who came up with the idea of control charts. Now, think about this. So if you have a process that that, let's say you're putting some sort of coating on top of a material, and you're worried about how thick it is, you don't expect every single one to be a perfect mirror image of the last product that came off of that line. There's going to be an average, if you sample enough, of average thickness of that coating, and that some are going to be a little bit thicker, some are going to be a little bit thinner. So in statistical process control, keeping this first point in mind, you can actually consider that process and say, okay, how much should I expect it to vary? That's the whole idea of statistical process control. And if you want to map this process over time, that comes into the idea of the control chart. So again, very, very simple concepts. Very, very simple concepts, but very, very profound, very, very profound effects from those concepts. So that's just a normal run chart, just giving some example for those. Now, Six Sigma actually became very popular in the United States with a company called Motorola. Motorola back in the 80s was one company that was actually outperforming the competition internationally in manufacturing, and this was a big deal back in back during the 1980s. A lot of the automotive industry had gone on a decline and was starting to pick back up, and other manufacturing, not just automotive, and Motorola was outperforming not just in the United States but internationally. And a lot of that success was attributed to them adopting Six Sigma early. So Six Sigma, actually started getting a lot of its foothold, at least in the United States, because of the success from Motorola. Now, one thing to keep in mind, a very important concept with Lean Six Sigma is this idea of variation. It's actually part of the name. That's what the Sigma comes down to in Six Sigma. So what is variation? So again, a couple of definitions. It's just a range of difference between statistical mean, so the mean, the average, and all the data points that are used to calculate that mean. Another definition, the extent to which a process performance varies around an average. So essentially you come up with a population or a sample population, and you get an average of some form of data, some piece of data on that population. Let's say heights of college students, and you take 100 college students and you find out how tall they all are. So you get an average height, statistical average height of 100 college students, University of Cincinnati college students, and you decide, okay, how, everybody isn't exactly the same height. That mean is just, a mean. It's just, the average. So you decide to look at how much they actually vary. That variation, that spread, is your standard deviation. And it's important because you can have two different populations, let's say University of Cincinnati and let's say University of Indiana, and have the exact same average. And that average, isn't totally representative of what's going on in that population until you look at other features, and one of the main ones is the variation, which would be the spread, and you find out that the people in Cincinnati all group together around that height, tighter than the people in University of Indiana. You know that something must be different in Indiana since they have a wider spread or a wider variation. So variation is represented mathematically by the standard deviation. So the standard deviation is the deviation from the average. Now here's another bit of an example, kind of goes back to what I was saying. Here you have male and female fulmars, and you're looking at the metabolic rate. And you can see the average between the two is not all that great. However, the standard deviation is almost double or more than double for the male fulmars than they are for the female, meaning the spread is much wider. So there's a tighter grouping around the females than around the males. So that's the power of standard deviation. It lets you know that this population is a lot less predictable than this population. And this is the formula for standard deviation. And when you think of this first definition, it actually mathematically looks the same. The range of differences, or range of difference between the statistical mean, and all of the data points that are used to calculate that mean. So when you consider that, this definition of standard deviation mathematically kind of, it makes sense. You can go, if anyone doesn't know how to do the standard deviation, you can do that, but you can kind of look at that equation and see that they kind of, has some intuitive meaning behind it. So let's go through an example. So there's this company that makes a high fiber cereal called Cullen Blow, and it is a very popular cereal and very successful, but they are running into some problems. And the executive wants to know what the issue is with the problem, how to make his customers happy. So he's in charge of the production line at Cullen Blow, and the customers have a complaint that the weight of the boxes are not predictable. They're very irregular, very sporadic in terms of the weight. And when he went to look at the weight of the boxes and looked at some of the complaints that the customers got, they ranged from 18 ounces to 14 ounces. So 2 ounces over, 2 ounces under was the span of the complaints, even though the box itself said they were supposed to be 16 ounces. Now, you probably didn't see a whole lot of complaints from the 18-ounce people, and I'm sure the 14-ounce people didn't really appreciate getting cheated out of some cereal. So that was the problem, that he were getting an irregular amount of weight out of each one of these boxes, so it wasn't predictable. In other words, there was some variation. Now, before we go on with this example, let's take a little sidetrack. I want to define a term because it's going to become important, and that term is a defect. Now, we can all think of what a defect is just in our casual conversation, but what is a defect in terms, just so we can come with a standard definition for this? So it's any process performance outside of defined specification. Okay, so that's going to be our working definition of a defect. So anything that happens to the product we're getting that basically we didn't ask for, that we didn't want it to do. So this would cover anywhere from a car door with no handles on it to a car door with the wrong coating of paint. Those are all considered defects. Now in Six Sigma, we're concerned with the defects per unit. A unit would be each product, and we want to see the total number of defects that are happening to units, so that would be DPU. Another thing in Six Sigma, we are concerned with things in the millions, per million, and that is how many defects do we see per million opportunities. Now, the way we calculate that is we take the DPU, defects per unit, multiply it by a million, and divide it by the number of opportunities. Or an opportunity would be, opportunity in the process of manufacturing it, or able to recreate that defect. In this case, there would probably be a weigh station or something at the Cullen Blow factory where there is an opportunity to make this particular defect, to actually put the wrong amount of cereal into the box. Now, upon hearing this complaint, it was probably very gut-wrenching news for the person in charge, that manager in charge. So they wanted to get to the bottom of that complaint. So what they did was they looked at cereals that weren't getting this complaint. There was all sorts of competitors that were also selling that cereal. So they wanted to say, well, how much variation is with their product weight. And what they found when they looked at this product weight, and they looked at several samples, and they found out that they were ranging just 1.2 ounces away from their average, or a range of 14.8 to 17.2 ounces. So it's a bit narrower range than our 14 to 18. All right, so this is going to become very important. So this is what the customer finds acceptable. And we found it simply by looking at our competition. So that's what the customer is expecting, and we're not doing that. We're going way wider than that range. And again, it's something where we actually measured that on the scale and came up with it. So what we did was this executive went on to collect some data off of his own line. He went out and got 72 boxes and measured how much they weighed. And what he found was, when he looked at the range of the weights, was, there were some that were as high as 18 ounces, some as low as 14, and there were several in between. And, this was a pretty disturbing number. Again, probably didn't help the stomach ache any. But, he saw all these, what we're going to call defects in the amount of the weight of his product. what he found in total was out of those 72 boxes, 24 were outside of the range. So 1/3 of his boxes, 1/3 of those boxes of Cullen Blow weren't within this industry standard or this industry range. So this acceptable range the customer wanted to see, 1/3 of the time they weren't getting it. Again, that's important. Again, also keeping in mind this industry range is also very important. So what did you do with this data? So, okay, you wanted to get this data and you wanted to make some sense of it, defects and all. So what he found was that the mean of all these boxes was 16.26 ounces. Not too bad. That falls within the range. It's, not that high off of what they're claiming of 16 ounces. The mode, was 16 ounces, and the median when running this data was also 16 ounces. So off of that alone, again, keeping in mind when I was looking at the population of college students, just looking at this in terms of those three stats, this doesn't sound like it's too bad. But again, remember the purpose of standard deviation. How big was that spread? What we found was that there was a standard deviation of 1.22 that he's getting from that small sample population of boxes. Okay, so this is where things start to get important. This is when we start seeing the importance of the name Six Sigma. Okay, so we look at this number of data observations. We got 72 boxes that we measured. We look at the number of defects that we found, and that was 24. So we can calculate our defects per unit. So our defects per unit, again, was 24 out of 72, or 0.3333. I truncated it to 2 decimal places, 0.33. And what we've, and this is, the defects per unit that we're dealing with here. Now, defects per unit, if we wanted to see this over the course of 1 million, it's defects per unit per opportunity, and we're just going to say it was one opportunity at that weigh station. Comes out to 333,333. So 1/3. So it's 1/3, and this again should make sense. So we found in the small sample was 1/3, 24 out of 72. And if we scale this up to 1 million, if we were going to produce 1 million boxes of Cullen Blow, we would expect to see that 1/3 scale up to over 300,000 boxes. So again, this is very, very important to keep this information in mind. So we'll have it all cataloged on the next slide. So that defects per million opportunities, we had a standard deviation of 1.22. Keep in mind, this is our industry range, or what our customer is expecting us to fall within, 14.8 to 17.2. Now, both of these together, our defects per million opportunities and that standard deviation, comes in to tell us how capable our process is. And this is important, and this is also going back to why this is called Six Sigma. This is a chart that shows how many defects per million opportunities you can have, and your level of Six Sigma, and what your process yield. In other words, how good you're actually doing, how capable you are of actually keeping the customer satisfied. And if we consider, again, with this standard deviation, and with this as our specification limits, where we want to operate within, what we are finding is that we are 2 standard deviations. We're operating at 2 standard deviations based on this limit and the specification. So that's 2 standard deviations out. And what we're finding is that we're only getting them 2/3 of the time. We're only giving our customer what they want 2/3 of the time, which makes sense. That's exactly what we found on the last slide. So we were having 1/3 defective product coming off the line, meaning 2/3 was coming out, and that's what it looks like if we base our Sigma level off of the specification limits, which is what the customer wants. Again, very important to remember, this is what the customer is expecting, and this is the variation we're giving them, and therefore this is where we're operating in the eyes of the customer. So this is where we're operating in the eyes of the customer. Now, the power of operating within Six Sigma if we were able to fit Six Sigma inside of this same specification limit, this is where we should be performing. This is the Six Sigma level. And our customer would actually be seeing 99.9997% good product at Six Sigma. So this is where we want to go. This is what this whole class is about. Being able to operate and maintain a Six Sigma level of performance inside of the specification limits with, that's given to you by the voice of the customer or what your customer is looking for. To give you a little bit more visual of this, this is a normal distribution curve, or just a generic normal distribution curve, with the mean being here, and then you get 2 sigma or plus or minus 1 sigma, which is 2 sigma, plus or minus sigma, which would be 4, and then you got 6 sigma all the way out here. And what we want is to operate with our specification limits to coincide with plus or minus 3 sigma or 6 sigma. Now, if we were to just ignore the y-axis, just pay attention to the x-axis, and we apply our scenario to this bell curve, this would be our specification limits. So we'd have an average here, where 16 is what our average, what we are trying to achieve. Our plus 3 sigma would be 17.2, and our minus 3 sigma would be 14.8, which means that this range is 6 sigma in between. 99.9997% of our product will land within our specification limit if we're operating at the 6 sigma level. In other words, there will only be 3.4 defects per million opportunities. So every time we come up with a million boxes of cereal, there will be 3.4 or 1.7 boxes above and 1.7 boxes below. Or I got that backwards, 1.7 boxes above, 1.7 boxes below, if we're operating at 6 sigma. So our customer at the 6 sigma will almost never see a defect. And the few times they have a defect, we can probably address that by giving them a new box of cereal. So this is the power of Six Sigma, and this is why it's actually called Six Sigma. So to summarize that, just a little known facts are some of the facts we went over. Six Sigma is a statistical-based methodology used to reduce variation and eliminate defects in business transactions and manufacturing processes. Variation is the range of difference between the statistical mean and all data points that are used to calculate that mean. That was the formula for standard deviation that we looked at. And a defect for our discussions is any process performance outside of the defined specifications. And the acceptable amount of variation is based falling within a certain specification. And that is probably one of the least emphasized things that you see in Six Sigma, that the specification limits have to be defined, and that variation is meant to fall within those specification limits. Okay, so this is Professor Cummings, and this was your overview of Six Sigma. In your next lecture, we'll be talking about the combination or the combining of Lean and Six Sigma as a continuous improvement methodology. So thanks for watching.